Welcome to Cookie's Maths and Science Hub. In today's video, we'll be exploring the concepts of vectors and scalar measurements. The difference between scalar and vector measurements is quite straightforward, but can be confusing for someone who's coming into the concept for the first time. Scalars are described with magnitude only. For example, a value like 5 meters is considered a scalar value or a scalar measurement. Vectors, on the other hand, are described with magnitude and direction. For example, using that 5 meters again, you would write 5 meters north, although it could be any direction, it just has to have a direction. So the fundamental idea here is that scalars are only magnitude, so they are just a number. It can be any value, it could be 5 meters, it could be 5 minutes, anything like that, whereas vectors also have a direction. Whether that's north, south, east, west, left, right, up, down, anything with any sort of direction. They get a bit more complex as we go into vector additions, but we'll discuss that later in the video, where they start to incorporate angles and such into their directions. Let's look at a few examples now of different measurements that fall under these two categories. So, as you can see, a lot of standard measurements fall as scalar measurements, such as time, temperature, speed, distance, mass, energy, and power. Whereas our vector measurements are things like velocity, acceleration, force, displacement, and weight. Just touching on two quickly, or a couple of examples. Speed and velocity. Now they're both measured in meters per second, but if it has a direction, it is velocity, whereas if it has no direction, it is speed. The same is with distance and displacement. Obviously, these are different terms and mean slightly different things, but they have the same measurement. So distance is meters, whereas displacement is meters and then some sort of direction. Let's have a go at identifying a few examples now with this idea in mind. I suggest you pause the video now and have a go at identifying these basic measurements as either vector or scalar quantities. Okay, let's make our way down the list. We have 15 meters per second north. So, the question to ask is, does it have a direction? In this case, yes, it has north. Therefore, this is a vector. The next one we have is 20 minutes. Now we know time is a scalar measurement, but we can also see that it has no direction. Therefore, it is scalar. Our next one is 3.47 kilometers. Now this could be distance or displacement, as it has some sort of length in meters or kilometers in this case. However, no direction is given, therefore it is scalar. Next we have 80 kilograms. Again, no direction, therefore scalar. Next we have 800 newtons down, N representing newtons in this case. Don't worry if you're not familiar with the letters, it's for different levels for everyone based on what they're working with in science. As it has a direction, however, we can see this is a vector. Next we have 15 meters north, 47 degrees east. This is one of those more specific examples I was talking about, but it is a direction nonetheless, and therefore it is, that's right, a vector. Lastly, we have 999 meters per second squared. Now, if you're a bit more familiar with some of the terms we use, you'll know meters per second squared is acceleration. Whilst this falls under the vector list, here we're only representing its magnitude. Therefore, because there's no direction, this would be an example of a scalar measurement. Because vectors have a direction, we unfortunately cannot add them simply like we can scalar quantities. This introduces us to vector addition. Now, to represent a vector in a diagram, and for these addition problems, we use an arrow. The length of the arrow tells us the magnitude, whilst the head of the arrow gives us the direction. It is important with using these arrows that you remember the scale of the arrows, and a ruler is a helpful tool when doing these additions. For example, if we were to have two vectors, one that represents 30 meters north, and the other that represents 5 meters south, then the 5 meter south arrow should be 6 times less in size than the 30 meters north, or the 30 meters north should be 6 times greater than the 5 meters south. This is important when we start to draw diagrams and add these vectors together. So, with that in mind, how do we add vectors together? Well, it sounds simple at first, but you must be careful as you draw them. So, making sure our arrows are scaled, all you need to do when adding a vector to another vector is connect the tail of that vector to the head of the other vector. So, if we look at that in a diagram, our first vector, let's not worry about any figures right now, is just this vector here. Then we have our second vector, which adds onto it, and maybe we have a third vector in this scenario as well that adds onto that. Now, in these scenarios, we're often working with things where we require the displacement, or from the initial point to the final point, and in those cases, we get a resultant vector, which is from our starting point to our finishing point. Let's look at some actual problems now using some numbers and discuss what strategies we can use to solve for this resultant vector. In these examples, I will be using the term displacement. Displacement is the measure of the change of one's position from their initial starting point, for those who are unaware or for those who need a refresher. So, in this example, we have Fred walks 5 meters north, then 3 meters south, and we're asked to find his total displacement. So, our two vectors in this scenario, we have one that's 5 meters north and another that's 3 meters south. Now, looking back at our example from before, when we discussed how to add vectors, we know we simply need to connect the tail of the second vector to the head of the first vector. So, this means in this case, they will overlap as one is going up and down in our diagram. As such, our resultant vector, which starts its tail at the starting point and finishes its head at the end point, is going to make up effectively the difference between these two vectors. Because we have 5 meters north, then 3 meters south, our resultant vector is equal to 2 meters. However, the key fundamental thing in vector addition is that our resultant vector also has direction. Now in this case, we can see we went 5 meters north, then 3 meters south. So looking at our resultant vector, which direction is it pointing in? North. So we would say our resultant vector is 2 meters north. And if you think about the problem, Fred is still 2 meters north of his initial point, hence his displacement is 2 meters north. Because it is a vector quantity, it requires that direction. Now, this second example is a little bit more complicated. You wouldn't expect to encounter this until advanced grade 10, grade 11 maths or physics. So, Amber walks 5 meters north, then 3 meters east. What is her total displacement? So again, we have our two vectors, one that's 5 meters north and one that's 3 meters east. So, using vector addition, we'll simply connect the tail of the second vector to the head of the first vector. So first they worked 5 meters north, then 3 meters east. Drawing in our resultant vector, you can see straight away that this isn't going to be as easy as a simple substitution, like it was for our first example. No, in these scenarios, you need to use Pythagoras. Now, if you need a bit of a refresher on Pythagoras, I'd recommend checking out our video on Pythagoras and trigonometry. Quick hint, trigonometry is about to come up as well. So, using Pythagoras for our unknown side, or our resultant vector in this case, it'll be equal to the square root of 5 squared plus 3 squared, which equals 5.83 meters. Now, much like in our first example, as it is a vector, we need the direction. Again, our direction is not as simple as just the reverse or, wherever the vector is pointing. So we need to use trigonometry to solve for our angles. In these problems, you'll usually be given two known sides. I would always recommend using the known sides given to you in the problem for finding the angle, as you never know when your Pythagoras calculation may have been incorrect, and this can lead to you using the wrong number and getting the whole question wrong rather than just a part of it. So in this case, from where our angle is, that is the angle of our resultant vector within the triangle, we have our opposite side and our adjacent side, which means thinking back to Sokotoa, we're going to use tan. So tan of our angle is equal to 3 over 5, which means tan to the negative 1 of 3 over 5 will equal our angle. That means our angle is equal to 30.96 degrees. Therefore, our final solution is 5.83 meters north, 30.96 degrees east, as we have moved 30.96 degrees away from that north line towards our east line on a compass. Thanks for watching. Hopefully now you have a sound understanding of vector and scalar measurements. Hope to see you soon.